The other question is, I read A Brief History of Time a long time ago. So I want to ask a couple of questions about that. So when the universe is contracting within Hawking's model, there is this proclivity, as you just pointed out, for everything to move from a state of relative disorder and dispersal to a state of relative order. And Hawking seemed to imply in that book that meant that the arrow of time was running backwards. But that puzzled me in two ways. And one would be that there could still be all sorts of random perturbations in systems that were collapsing. And the other is that it seems to me that the notion of quantum uncertainty also disproves the idea that the arrow of time would run backwards in some deterministic way, because there's no. So that's the question on the Hawking side. So,
yep. So let me answer those in reverse order, because it's worthwhile noting that Hawking himself changed his mind on this point regarding the reversal of the arrow of time upon contraction. So much of your concern with that is actually borne out by our views as well. So nobody really takes seriously this idea anymore that the arrow of time would reverse. But the first question of how do you get the ordered structures like stars and galaxies from this Big Bang beginning is a deep one. And I believe that we have some insight into that, which more or less goes like this. The Big Bang happens, the universe starts swelling rapidly, and the energy that drove that expansion then disintegrates into a bath of particles that fills space. Now, you might think a bath of particles filling space, that sounds disordered. That sounds really high entropy, like the gas in this room. The particles are filled out through the room. Perhaps things would just stay that way, and there would never be clumps of particles. And what changes is when gravity matters, and it does on cosmological scales. It doesn't matter in this room. Gravity is irrelevant to the air molecules in this room. But gravity does matter if you have enough particles filling space, and that certainly happens with the universe as a whole. And what that means is gravity starts to pull little inhomogeneities, a little denser knot of particles here, a little less dense over here. The denser one starts to pull in more particles. It gets denser still. And because it's denser, its gravitational pull is yet stronger, and it pulls in more particles. And ultimately, you get these locations where particles begin to implode in on themselves, getting hotter and denser, ultimately igniting nuclear processes, and a star is born. And the beautiful thing about this, and this is incredibly subtle, but the beautiful thing is this formation of the star is indeed a drop in entropy. A star is more ordered than the original configurations, but in the formation of the star gives off heat and light that emits entropy to the wider environment. I like to call this the entropic two-step. Entropy goes down in the formation of the star, but it goes up in the wider environment. And overall, the entropic balance works. The overall entropy goes up, even though you get a pocket of order in the wake of that entropic increase.
Okay, well, human beings do that too.
Exactly. That's what we do, right? So, we eat food. We take in these orderly sources of energy. We burn that fuel to allow biological processes to take place, keeping our entropy low. But in the process, we go off heat. We expel waste. And if you take account of that, then the overall entropy of us and the environment does go up. But our entropy is able to kind of thumb its nose at the second law of thermodynamics, at least while we're living, and are able to keep our entropy stable.
Mm-hmm. So let me ask you a question about that initial clumping. It occurred to me, I'm sure this isn't an original idea, that so if that initial state immediately after the Big Bang can't be homogeneous, and perfectly homogeneous, because quantum uncertainty with regards to the positioning of the particles would mean that there would be some lack of homogeneity. And the explanation you gave seems to imply that even minor deviations in homogeneity would start a clumping process, would begin the clumping process, and then once it starts, it's going to capitalize on itself. And so is the lack of homogeneity after the Big Bang a direct consequence of quantum uncertainty with regards to the position of the particles?
It is. It is. That's exactly right. And it's even more than just an interesting idea. What we've been able to do, and these are calculations that go back to the 1980s, we've been able to model the early universe mathematically using quantum physics, using Einstein's general relativity. And we've been able to calculate how the uncertainty in the positions and the energies and the speeds of the particles should affect the environment. And we've been able to calculate that it should cause tiny inhomogeneities as well in the temperature of the night sky and the temperature of space, which means that if you could measure the temperature of the night sky to adequate precision, you should be able to test the prediction. And this is what we have been able to do with the so-called cosmic microwave background radiation. This is heat left over from the Big Bang. And starting in the 1990s with ever greater precision, we've used space telescopes and other devices to measure the temperature of space. And the agreement between the theoretical predictions and the observations is so incredibly accurate that to see the error bars in the measurements, you have to magnify them by like a factor of 500 so that the naked eye can even see them on the graph. That's how tightly there is an agreement between the mathematical calculations that we humans do, these little biological systems crawling around this planet, barely coming of age in the Milky Way galaxy, have been able to calculate conditions billions of years ago and compare them to observations, and they agree to spectacular precision. This is one of the great triumphs of modern science.
I see. So you could detect lack of homogeneity in the background temperature, and that was also indicative of lack of homogeneity in terms of dispersal of particle density.
Exactly.
Yeah. Oh, wow. Okay. That's very cool. All right. So that's so interesting, because that implies as well that or indicates that quantum uncertainty makes it impossible for there to be a homogeneous distribution of particles. There's going to be asymmetries emerge. And those asymmetries, right, and then the asymmetries expand up until they manifest themselves at a cosmological level with stars and galaxies and those large filaments that the galaxies appear to congregate in. And wow, okay, so that's how that comes about.
We are the progeny of quantum uncertainty writ large across the universe. Right.